The characteristics of the motion of an object can be described by, or interpreted from, graphs. We will find that the velocity of an object can be calculated from its position versus time graph, and the acceleration from its velocity versus time graph. Consider a car moving at a constant velocity in the positive x direction. We can plot the position as a function of time, and in the case that the car maintains a constant velocity, the position time graph is a line. But suppose we were given the graph without witnessing the motion. How would we extract information from the graph? The velocity is given by the slope of the position time graph. We can calculate the slope by drawing a right triangle with a portion of the linear curve as the hypotenuse and the other two sides parallel to the x and t axes. The slope is then calculated as the rise over run, which, in the case of a position time graph, is delta x divided by delta t. Note that delta x over delta t is the definition of average velocity. In the case of constant velocity, as in this case, the average velocity is equal to the instantaneous velocity. Referring to the triangle we've drawn, x final equals 30 meters, x initial equals 10 meters, time final equals 3 seconds, and time initial equals 1 second. And the velocity is equal to 10 meters per second. Note how the units work out. Meters from the vertical axis over seconds from the horizontal axis, so that the units of velocity, meters per second, fall out naturally when calculating the slope. Also notice that, since the graph is a line, the slope, and therefore the velocity, is constant throughout the motion. In general, the motion can be more complicated with stopping, starting, and changing of directions. All of this is reflected in, and can be extracted from, the position time graph. In this example, there are 4 linear regions of the graph with different slopes. In region 1, we draw a triangle to find the slope as rise over run, or delta x divided by delta t, which equals 15.0 meters divided by 0.75 seconds. These values were read from the graph by estimating their lengths along their respective axes. In this case, the velocity is equal to 20.0 meters per second. In region 2, delta x equals 0 meters, and the slope is 0, which should be immediately apparent since the line segment is horizontal. What does this mean? If delta x equals 0 meters during that time interval, it means that the car was not moving, or at a dead standstill during that time. In fact, it was stopped at x equals 40 meters for 1 second. In region 3, we calculate the slope, being careful to use the correct signs. In this case, delta x equals negative 15 meters, and delta t equals 0.75 seconds, giving v equal to negative 20 meters per second. In this segment, the car had reversed direction. Finally, in region 4, the slope is again 0, and the car was stopped at x equals 0 meters. Often, the position time graph is not composed of simple line segments, but rather curves from which the slope cannot be directly calculated. In this case, you can find the velocity at a point on the curve by first drawing the tangent line to that curve at that point. For instance, to calculate the velocity at this point, we draw a line segment to the curve at that point and then calculate the slope of that tangent line. Since this value is calculated at an instant in time, it is equal to the instantaneous velocity. For the next point, the tangent line is horizontal, and we should immediately conclude that the velocity is 0 at this point. Finally, for this last point, we see that the slope of the tangent line is negative, and therefore the velocity is negative. Another common graph that describes the motion of an object is the velocity time graph. The slope of this graph is delta v divided by delta t, which is equal to the acceleration. This particular graph is composed of 3 line segments. Reading the values from the graph, in the first region, the slope is 30 meters per second minus 10 meters per second divided by 1.5 seconds minus 0.5 seconds. This equals 20 meters per second squared. Again, note that the units of acceleration work out naturally. In region 2, the slope is 0. What does this mean? It means that delta v equals 0, which means that the velocity is not changing, and therefore the acceleration is 0. Finally, in region 3, we find delta v equals negative 7.0 meters per second and delta t equals 1.2 seconds, giving the acceleration equal to negative 5.8 meters per second squared. As a final remark, the velocity time graph need not be composed of simple line segments, but rather a curve of some sort. In this case, in analogy with our treatment of the position time graph curve, you need only draw a line tangent to the point at which you want to know the acceleration. The slope of the tangent line is the acceleration at that point. In summary, the velocity of an object can be calculated from the slope of its position versus time graph. The instantaneous velocity can be calculated from the slope of the tangent drawn to a point on its position versus time graph. The acceleration of an object can be calculated from the slope of its velocity versus time graph. And finally, the instantaneous acceleration can be calculated from the slope of the tangent drawn to a point on its velocity versus time graph.